Hello everyone and welcome to CSEN 1001 Computer and Network Security. This is Dr. Amr Al-Mouki. In this lecture we're going to start discussing a new topic, which is user authentication and key distribution. We have discussed before message authentication, which is about how to authenticate the origins and the contents of a message. The topic of today is about how to authenticate a user, how to make sure that a user is who they claim they are. To put it in a more general way, how to verify that any entity in the system, whether it's a client or actually also whether it's a server, that they are who they claim they are. This is the topic of user authentication, and associated with it is the topic of key distribution. That's why we're going to discuss them jointly. In many systems, when you are authenticating the user or authenticating the entity in the system, you want also to exchange a key so that this key can be used for all cryptography matters that follow. For example, the encryption, generating a message authentication code, or anything like that. Okay, and so what we will be doing in this topic is that we will start with more of a historical perspective. We will see some classical or traditional user authentication mechanisms, and then we will proceed to see the state of the art, what is actually used today in terms of user authentication. So we'll start from scratch. What is actually user authentication? It's the process of verifying an identity claimed by or for a system entity, and we perform user authentication over two steps. There is the identification step and there is the verification step. Basically, when we want to do user authentication, before even identification and verification, there has to be a registration step where you register your credential in a system, in a backend or in a server somewhere. And then when you want to verify or you want to authenticate yourself to that system, you present your credential to that system, which is the identification step. You specify the identifier. And then the verification step is where you bind your identity to the identifier. You say that this username, for example, belongs to this password. And so you get authenticated by the system. When it comes to methods of user authentication, we can actually categorize them into four main categories. There are so many types of user authentication mechanisms, but we can categorize all of them into four categories. And it's based on what the user actually presents to the system. And the categories are something that the user knows, which is, for example, the password or the PIN number, something that the user has or possesses. This is when you have a special access key card, for example, that you scan on a RFID reader to get in, or you have a smart card, for example, or in modern authentication system, when you want to do persistent user authentication, you have something called a token. And this token is given to the backend every time you want to access it. Okay, in this particular category, there used to be something called an Rsa Key. It's a small card that has a screen on it, and the screen displays a number. The card generates the number locally every period of time. And when you want to gain access to the system, you have to look at the card, see what number is displayed, and then you write it on the portal. Okay. The third category of user authentication is something that the user is. This is the category of static biometrics. Okay. These are physical features of the users that do not change with time. And they include things like fingerprint, retinal scan, iris scan, facial recognition as well. Any static feature of the user can actually be used as a static biometric. Okay. And the fourth category is the category of dynamic biometrics, which can include something that the user does. Okay, this can be voice recognition, a hand signature, or a gesture, for example. There are even methods for user authentication using something called gait, which is basically, it's GAIT, which is basically the way you walk. Okay, so there are systems now that try to do what is called gait recognition, which is to recognize your walking pattern to do authentication, for example. We'll discuss these methods in details later, but this is just an introduction to the four categories of user authentication. In any user authentication system, we are concerned mainly with two security services or features, which are confidentiality and timeliness. For confidentiality, you want to protect the session keys, you want to protect the outcome of the user authentication, and timeliness is concerned with the most important attack on user authentication systems, which is called the replay attack. In the replay attack, the attacker basically captures a message that the user is sending to the back end and replays it later. If this packet, for example, contains a password, then the attacker can just actually capture this packet and replay it later to the back end, which is why it's not very advisable to have an authentication system whereby the client sends the password, even if it is encrypted, because even if the packet is encrypted, still the attacker can capture it and replay it later, even if they do not know the key. It's sufficient that just the server or the backend knows the correct key so that they can be able to decrypt and check or verify that this is the correct password. So even if the attacker doesn't know the key, they can still replay the message and gain access to the system. So to prevent replay attacks, there are three main countermeasures: sequence numbers, timestamps, and what is called the challenge response system. Sequence number is when you have a sequence number in the packet and it counts increasingly. In this case, if you're for example expecting a packet with sequence number X and you receive a packet with sequence number X minus 1, then you know that this is an old packet and you reject it. With timestamps, every packet will have an expiration date, and so if you receive a replay after the timer has expired, then you will reject it, and obviously this needs synchronized clocks. The final method, which is the most prevalent one, is called the challenge response. In this case, when you want to do authentication, you ask the server for a challenge. The server sends you a challenge. So as you see in this figure, the challenges are: R can simply be a random number that is generated just for this exchange. When you receive the challenge, you will generate the response. And the response is based on R, okay? And has to be based also on the password or the credentials that you know. So it can be, for example, the hash of R concatenated with the password. In this case, only Alice will be able to generate this response because only Alice knows the password in this case. And so she generates the response and sends it back to the host or the server, who can actually verify that this is the correct response because the server will know R and will know the password as well. If Alice wants to do authentication a second time, she has to ask for a new challenge from the server. That means the challenge is only valid for a single exchange and it is thrown away after that. So a replay attack in this case will not actually be possible. The only problem with the challenge response mechanism is that it requires that the server be online at the time of this exchange. Okay? You have to receive a challenge from the server to be able to do a challenge response. Sequence numbers and timestamps, they do not have this requirement, and so challenge response mechanisms are recommended in the systems that actually have online servers, but in other cases you can rely on sequence numbers and timestamps. Okay. When it comes to key management and distribution, we are going to discuss it concurrently with user authentication because as the outcome of the user authentication, there might be a need to exchange a key, and the key will be used to do all the cryptography functions later in this exchange. Okay. Obviously, with the keys, you want to have frequent key changes so that you reduce the chance of a successful brute force attack. Okay. So you want to have a key, whether it's a public key or a symmetric key, and you want to renew it every period of time. That depends on the length of the key and depends on how critical the data that you want to protect is. And based on that, you determine what is the period for actually refreshing the key. But this is a very challenging task because if you just have actually 1,000 devices in the system, okay, and they all want to talk to each other, then the number of keys that will be exchanged can be calculated according to this equation. It's 1,000 multiplied by 999 over 2, which is approximately 500,000 keys. And this is only if we're doing even node level encryption, which is encryption at the level of the device. If you're going to do encryption at the level of the applications, which is more likely, then every pair of applications will need to have a key. And so suddenly these 500,000 keys can become 50 million, can become 100 million keys in a very short period of time. And so the key distribution task is actually quite challenging due to the number of required keys that need to be exchanged. And so typically what systems do is that they have a hierarchy of keys. At the top of the hierarchy, there would be something called the master key. The master key is afforded the highest level of security, and it is exchanged once, and it is not actually used to encrypt or decrypt actual data. Okay, the master key is mainly used for authentication and for actually also generating what is called a session key. This is the lower level of the hierarchy. And so the session key is typically a temporary key. It's afforded a lower level of security. And this is the one that is used to actually encrypt and decrypt data. For example, the WhatsApp system, as we will see in a later lecture, the WhatsApp system has something called a long-term key. This is the one that you exchange with the user that you want to chat with. And using this session key, there is something called the key derivation function that will generate, using this long-term key, there is a key derivation function that will generate another key that will be used to encrypt packets. And in WhatsApp, this key derivation function actually rotates the key in every message that you send. So the key that is generated is only used for a single message, and then it is rotated so that you generate a new key to encrypt the new message. And the rotation function or algorithm is synchronized between the two ends of the chat. And so they are both synchronized to the same key in every time so that they can encrypt and decrypt. This is how end-to-end encryption is actually done in WhatsApp. So we can now start our, let's say, historical lesson. And we will start with a classical user authentication method that is called the Needham Schroder protocol. It's one of the older ones and one of the most widely used ones. And in fact, many user authentication systems rely on the Needham Schroder algorithm or build on it. Okay. The Needham Schroder protocol uses only symmetric encryption. So it was at the time where everything or most functions in the system were done using symmetric encryption, and the Needham Schroder protocol is no different. Before we actually discuss this protocol, there is an important thing to mention here, is that all user authentication methods, whether they are using symmetric encryption, whether they are using public key cryptography, whether they are old or new, they all rely some way or the other or on having a trusted third party. Okay, and the only difference is sometimes you require this trusted third party to be online during the exchange, during the user authentication phase. The Needham Schroder protocol is an example of that. And sometimes in other systems, the third party can be offline during that time, as we will see. Okay, but there has to be a trusted third party. And the reason is you are communicating with a stranger, and you are communicating blindly. You don't actually see the stranger on the other end. And so you have no reason to trust that they are who they claim to be. Okay? They can be an imposter. They can be someone claiming to be the person or the entity that you want to actually communicate with. And so you have no reason to trust that entity. Okay? And so you rely on a trusted third party. You trust that third party to verify the identity of the person that you are actually talking to or the entity that you are talking to. In the Needham Schroder protocol, this trusted third party is called the Key Distribution Center or the KDC. And here, before anything starts, every entity in the system must have exchanged a master symmetric key with the KDC. So A will have KA, okay, which is a symmetric key exchanged beforehand between the initiator, between A and the KDC, and B will have KB, which is a symmetric key between B and the KDC. So KA is known only to the key distribution center and A. KB is known only to the key distribution center and B. Okay, so this happens before anything starts, and how these symmetric keys are exchanged is not part of the Needham Schroder protocol. It is actually assumed that they are exchanged in a secure way, and the keys are secure. No one knows them except the entities that are involved. So if this is the case, then the protocol starts with the initiator A sending to the KDC this message, which includes the ID of A, the ID of B, and a nonce. A nonce has a random number used only once, so A generates a nonce just for this exchange. The key distribution center, upon receiving message 1, will reply with what you see in message 2. It is something encrypted with KA. This something has actually two parts. Let's actually divide them. They are this part and this part. If you take the first part, you see here, this is the ID of A, the ID of B, and the nonce. So the exact same message that was sent in step 1 is returned back to A in step 2. Concatenated with them is KS, which is the symmetric key that the KDC will generate so that A can use it to communicate with B. So KS is the session key. this is the key that A will then use to communicate with B. It's not used for the KDC to communicate with A. It is used for A to communicate with B. Okay, and all of this is obviously encrypted with KA, the symmetric key that is exchanged between A and the KDC. And concatenated with this part, there is another part which is KS concatenated with the ID of A, and it's encrypted with KB. Okay, so this is sent, and all of this part is actually sent to A, encrypted with KA. So A will be able to decrypt and obtain the two parts, but the second part here, which is KS concatenated with the ID of A and encrypted with KB, this part A will just obtain it as it is. It will not be able to decrypt it because A doesn't have KB. Okay, so what's the purpose of that? Why would the KDC send something to A that A will not actually be able to decrypt? This is actually called a ticket. And this ticket is what A will forward to B in step 3. Okay, so A just actually takes it as it is and forward it to B in step 3 so that B will also have the symmetric key. And after that, in step 4, B sends to A a nonce encrypted with the session key KS, and A responds with something that is a function of the nonce, for example, the hash of the nonce, also encrypted with the same symmetric key KS. Now let's examine where does the authentication features or aspects take place. First of all, this protocol includes several challenge response mechanisms used for authentication. For example, A sends a nonce in step 1, and the KDC sends the nonce back in step 2 encrypted with KA. This is the first authentication step that happens. When the KDC returns the nonce back to A in step 2 encrypted with KA, only the KDC could have done that because only the KDC has KA. And so the response that is sent back from the KDC to A verifies that the KDC is actually the one who is talking to A. So A has now authenticated the KDC using the challenge response in steps 1 and 2. Okay? When A sends the when A sends the ticket to B in step 3, B will also verify that it is actually that this ticket is actually generated by the KDC because it's encrypted with KB. And so B will now trust that this symmetric key is an authentic one, that it has been generated by the KDC because it's encrypted with KB and only the KDC has KB. Okay, so the only remaining part is for B to authenticate A. So, and also for A to authenticate B. So the nonce that is sent back from B to A in step 4, nonce N2, which is a new nonce, this authenticates B to A. Because what does this message actually say? It says that B must have decrypted the packet correctly in step 3, thus obtaining the symmetric key KS. Therefore, it was able to decrypt and send the nonce in step 4. If it wasn't B, then it would not have KB, and it wouldn't be able to decrypt this packet and obtain KS. And so A will respond with the response here, which is a function or the hash of N2 encrypted with KS, thereby authenticating itself to B as well. So now B authenticates A. Now B knows that A must have had KS, because if it didn't have KS, then it wouldn't be able to decrypt the nonce in step 4, obtain the nonce, and generate the response in step 5. In order for A to do that, it must have received KS from a step before, and according to the protocol, this is only possible if the symmetric key is sent to A in step 2, encrypted with KA, so it must have been A, the one that has actually received this symmetric key. So the protocol allows everyone to authenticate everyone else, and after that, they can actually start communicating with each other using KS. Okay. So this classic protocol has seen wide use in its time, and it is a reliable protocol except for one very widely known problem, which is the exposure of old session keys. Typically, KS, the symmetric key, will not actually be valid for a long period of time. It is used for a session, so it is used for a period of time, and when A wants to communicate with B another time, it has to obtain a new session key, meaning that it has to repeat this entire exchange. So, in most systems, Expired keys are not afforded much security. It can be that it's not afforded any security at all. And so it is possible that in some systems, an attacker will get hold of an old expired session key, KS, a key that has been used before, but it is no longer valid. The session is over. And so KS is not protected. And so maybe the attacker gets a hold of it. Okay? If the attacker gets a hold of an expired session key, in addition to the message 3 that was used to send it, then the attacker can simply replay message 3 to B, and they will be able to authenticate themselves to B. Because what will happen in this case, if B cannot recognize that this is an expired session key, then B will just think that this is a new session key and it will proceed with sending the nonce in step 4. Okay, and in this case, if the attacker knows the expired session key, then the attacker will have KS and will be able to generate the response in step 5, thereby completing the authentication cycle and authenticating themselves to B. You have to note that B never communicates with the KDC in this protocol. B actually relies on A for authentication. Okay? And so if it's an expired session key and the attacker has hold of this expired session key in addition to message 3, then they will be able to execute this replay attack. And the condition here is that B also will not recognize that this is an expired session key. So B doesn't keep track. In many systems, keeping track of expired keys is out of scope of the application. Some applications do it. For example, if you go to Facebook and enter an old password, the Facebook server will actually tell you this is an old password. So it must be that it's because they keep a list or keep track of the expired passwords. But in many other applications, they don't do that. And so an expired session key will actually work. So this replay attack succeeds because there is nothing in step 3 that ensures that this is a fresh packet or this is a fresh exchange. This is why the replay attack actually succeeds. So we will see now 2 variants of the Needham Schroder protocol that deal with this problem. We will see an improvement using timestamps, and we'll see an improvement using nonces. So this slide here shows you the improvement using timestamps. So it starts also with K sending to the KDC the ID of A concatenated with the ID of B. Then the KDC responds with a similar response to the one that we saw last time, a big chunk encrypted with the symmetric key between the KDC and A. And this chunk includes the ticket. So this here is the ticket and includes a part that can be retrieved by A. So this is the only part that A will be able to read because the other part is encrypted with KB. So it includes the symmetric key KS, ID of B, and the time stamp. The time stamp is basically the expiry date. So the time stamp is also included in the ticket here, and it is the validity of the ticket. It's how long the ticket will actually be valid. And the ticket also includes, so this here is the ticket. The ticket also includes the symmetric key and the ID of A, and all is encrypted with KB. So obviously A will not be able to decrypt that, but will forward it just as it is to be in step 3. And then steps 4 and 5 are similar to the previous versions, another challenge response mechanism to verify B to A and B to B. Okay, so how does this actually fix the problem? Consider what happens when an expired session key is made available to an attacker, and now the attacker wants to try and replay message 3 just as in last time. Now the problem here is that the timestamp would have expired. So if the session key is retrieved after a long time and the time has expired, then once the attacker replays message 3, B will be able to detect that the ticket has expired, and so the session key in the ticket has expired as well. And so it will be able to detect that this is a replay and will not be fooled as in last time. So the timestamps, this is actually the intention of the timestamps. And if they are built this way, they might actually fool or they might circumvent a replay attack. But then the challenge is how long the expiration date should be. If you want the authentication to be persistent, that means you want to give A access to talk to B for a long period of time, then obviously the timestamp should be long. The expiration date should be long, which gives a high chance for a replay attack to succeed in this case, because during this time, the attack would actually be successful. Okay, if the expiration date is too short, then A and B have to repeat this protocol every time they want to talk to each other. Another problem is the timestamps require synchronization among the clocks of all the entities so that they make sense. When the KDC generates a timestamp for the packet or for this exchange in step 2, it sends it to both A and B. So now A and B know how long this exchange will last for. But A and B, in order for this exchange to make sense, they have to be seeing the same time. They have to be seeing the same clock, basically. And so clocks have to be synchronized. This is actually not an easy task because even if you just actually send the times to each other and somehow find a way to synchronize the clocks, any hardware clock will drift with time. Okay? So with time, they will start to become slower or become faster. And so over time, they will start actually seeing different times. That means that it is possible that in one entity of the system, for example, A, will be seeing time that is ahead of B. So A might actually be seeing that the ticket has expired, while B has a clock that is behind, so it thinks that the ticket is still actually valid. So in this case, the attacker might actually have a window to replay the message during the time when the message has actually expired, and so the attacker is able to obtain an expired session key and replay message 3. And because the clock of one entity of the system is delayed due to just normal hardware issues, this attack would succeed in this case. And this attack is called the suppress replay attack, and it happens when the sender's clock is ahead of the recipient's clock due to normal drifting of clocks, and this is basically the issue with timestamps. The other improvement is using nonces, and the protocol is a little bit different in this case. So we start with A sending to B, not to the KDC. So it sends the ID of A and the nonce that A generates. And now B will not respond back to A, but rather it will respond to the KDC directly. So it will send to the KDC the ID of B and a new nonce in B, and it will send something encrypted with KB. This something is the ID of A, the nonce that A has sent to B in step 1, and a timestamp or a period of validity for that ticket. Okay, and so the KDC will obtain that and will decrypt it and will get the ID of A and will get the nonce and will get TB and will send to A in step 3 something that is encrypted with a KA. Okay, this something is the ticket. Okay, this part which is encrypted with KB, and will send the ID of B and A, the symmetric key, and the timestamp as well. And all of that is concatenated with the nonce that B has sent in step 2. And so after obtaining this part, A will decrypt and will get the ticket and send it just as it is to B in step 4, and will send also the nonce B encrypted with KS as well. Let's check actually where are the authentication steps. Here, the challenge response mechanisms are actually done a little bit different. The nonce that A sends in step 1, NA, is sent to the KDC in step 2 and returned back to A in step 3. This is the three-way challenge response. So the nonce is sent to B and returned from the KDC. In order for this to happen, then it must be the case that the KDC has received it correctly and was able to decrypt it. That means the KDC is a legitimate entity because it must have KB in order to obtain an A. And it is the KDC that sent it to A because it's encrypted with KA. So it's a three-way challenge response. In addition, the nonce that B sends in step 2 is sent from the KDC to A in step 3 and is encrypted with KS in step 4. This indicates that it must be A who is generating this response because only A will receive KS in step 3 because it's encrypted with KA. Notice here that this is the only step that has KS other than step 4. So it must be A that received the KS, and it must be A that generated the response in step 4. Okay, so everyone again authenticates everyone else. Now, if you notice, there is still a timestamp here. There is TB that is generated by B in step 2 and sent to the KDC, and the KDC forwards it to A, and A forwards it to B in step 4. Okay. So if there is a timestamp, doesn't this mean that the system is still actually vulnerable to a suppress replay attack, just like last time? The answer is actually no, because in this case, the timestamp is done differently. It is generated by B and only checked at B. Okay, so B will generate it in step 2, and B will be the only one responsible for checking that the ticket in step 4 is a valid one. Because replay attacks will happen at B. The attacker will want to actually send the message in step 4 or replay the message in step 4 to B. And so it is the responsibility of B in all cases to check that this is a replay. And so this is exactly what happens. B generates the timestamp in step 2, and B will be the one responsible for validating that this ticket has not expired. Okay, so suppress replay attacks in this case are not possible because there is no requirement that the clocks are actually synchronized. If the clock drifts, then still it is only B that is checking the clock, and so there is no problem there. In some systems, you want to do only one-way authentication. These are typically the systems where the sender is sending a message to an entity that is not necessarily online. For example, when you're sending an email, if you're sending an email, you cannot actually enforce, or you cannot actually force the recipient to be online when you're sending an email. That defeats the purpose of the application itself. And so in this case, you want actually to have a one-way authentication method where you are authenticating yourself to B, and you're relying that if B is the legitimate entity, it will be able to decrypt this email. And so one example of a one-way authentication protocol works as follows. A will start by sending to the KDC its ID, the ID of B and N1, and the KDC will send to A the ticket, just like last time, okay, and the symmetric key ID of B and N1. And in step 3, the ticket is forwarded to B together with the encrypted message, and the message is encrypted with KS. If B is a legitimate entity, then it will be able to decrypt the ticket and obtain KS, therefore being able to decrypt the message as well. So this is a one-way authentication system. There is still a challenge response taking place here, but you cannot actually do the challenge responses in steps 4 and 5 because B will not be necessarily online in this case. All these protocols that we have been discussing are using symmetric key encryption. With the advent of public key cryptography, things changed, particularly with the invention of the Diffie-Hellman algorithm. And with the Diffie-Hellman algorithm, we know exactly that there is a simple way to exchange a secret without actually sending the secret explicitly. So the entities send the public keys to each other, and they calculate a secret locally without having to send the secret to each other. And so if this is the case, then it seems that the problem is solved. We can actually exchange the key without having to worry about how the key is encrypted or any of that. But from the discussion in Diffie-Hellman, we know that Diffie-Hellman, or the plain form of Diffie-Hellman, suffers from a very well-known problem, which is the man-in-the-middle attack, where the attacker intercepts the public keys, generates public keys of his own, and sends them to the two parties, thereby fooling them that they are talking to each other, while in fact they are actually talking to the attacker. And so if you are using public key cryptography for key distribution, the challenge becomes how to securely distribute the public keys. And if you have the example that you see in this figure, let's say A wants to communicate with B, so it just sends it its public key and its ID, just like we would do in Diffie-Hellman. And the idea is B will respond with a message, or with a symmetric key that is encrypted with the public key of A, or will respond with its own public key if it's using Diffie-Hellman, so that it can calculate the secret. This exchange in particular, as we know, will be vulnerable to a man-in-the-middle attack, where the attacker will intercept this message and forward its own public key to B, and B will forward its public key to the attacker, and the attacker will be able to obtain the secret key and communicate with both entities secretly. If the public keys are in fact securely exchanged, if we assume that A and B already know each other's public keys, then we can have a protocol like the one that you see in the slide. So A will send to B a nonce and its own ID encrypted with the public key of B. We're assuming that it's known to A. And B will send back to A the nonce and concatenated with a new nonce encrypted with the public key of A. A will send the nonce encrypted with the public key of B, and then will send the symmetric key digitally signed and encrypted with the public key of B, so that the exchange is now complete. Okay, there are two challenge responses to do authentication, and then the symmetric key is exchanged. So now we have to solve this challenge. How do we exchange the public key of an entity securely? And the idea is, how do we make sure that an entity that is claiming to own this public key is verifiable, that this entity indeed owns this public key? Um, this is not something that we have discussed before. So far, we have been saying that the public key is public, everyone knows it. But now the challenge is how to bind this public key to an entity. The straightforward solution is to have what is called the public announcement. You have something online where everyone just actually registers their public keys and their ID, and this announcement or this directory is available to everyone. This is obviously not secure because it's vulnerable to the same thing. Anyone can actually register a public key and claim to be any entity that they like. And so you need this directory, the centralized directory, to be a trustworthy system, to be secure, to have some security measures to validate the identities of the people that register in it. And the first version that we will discuss of that is something called the public key authority. So it's still a centralized authority. It has the properties of a directory, but it has security mechanisms in place to verify the identities of the users. So if there is a public key directory, the protocol becomes as such. If A wants to communicate with B, it will start by going to the public key directory and asking it for the public key of B. So it will send a request and a timestamp to prevent message 1 from being replayed. Okay. The public key authority will send back this response in step 2, which is the public key of B, which is the parameter that A requests, and the request and the timestamp, everything digitally signed. Okay. This is the private key of the public key authority. So this is sort of a certificate. This is something that is digitally signed by the public key authority. And if the initiator trusts the public key authority, then it trusts that the signature is valid. And now it has obtained the public key of B. And if it has obtained the public key of B, then it can proceed with the message in step 3 by sending a nonce ID encrypted with the public key of B. So now B wants to do the same. B wants to obtain the public key of A in a secure way. So it sends also a request in step 4 and obtains a certificate of A in step 5. So B will now obtain the public key of A and can respond back with the nonce N1 and the new nonce N2 encrypted with the public key of A. And A will send the nonce N2 encrypted with the public key of B. And so everyone now has authenticated everyone else. And so if there is a public key authority, then it is the trusted third party that A and B will rely on to exchange each other's or to obtain each other's public key in this case. And if they obtain the public keys, then they can proceed with Diffie-Hellman, or they can use RSA to encrypt the symmetric key or whatever they want. So now it seems that the problem is solved. We still have a trusted third party, the public key authority, but now we are using public keys instead of symmetric encryption. So it seems that the problem is solved. But the only problem left for us to discuss now is that the public key authority has in fact to be online all the time. It has to be active all the time. So far, this has been a common feature with all the third-party systems that we have been discussing, either in the Needham Schroder protocol, the original one, the two variants. Even in the one-way authentication, there was still a KDC that needed to be online for A to contact it. It's actually B is the one that we don't require to be online. If it's a public key authority, even if we're using public keys, we are still actually requiring the public key authority to be online. So the final method of authentication that we will discuss in this lecture is one that does not require that the third-party system, the trusted third party, to be online at the time of the authentication. And this is the one that is widely used in the internet, which is called the certificate authority. And the system is called the public key certificate. The idea is we want all the security features associated with the public key authority without requiring that the public key authority be active or online at the time of the exchange. And so quite simply, what will happen is all the information that would need to authenticate A will be put in a certificate and sent to A. And so A will register its public key and its identity at the certificate authority and ask for a certificate. The certificate will include the public key of A, its own ID, and a period of validity, which is the time, how long the certificate is valid for, and everything is digitally signed by the certificate authority. So this certificate will be given to A. So now A has CA, B will do the same, and now B has CB. Now, A and B will have their own certificates. Whenever they want to talk to each other, they can just exchange the certificates without the certificate authority needing to be online. So they obtain the certificate once, and whenever they want to authenticate themselves to anyone, they can just give them the certificate and show them that the information is digitally signed by the certificate authority. The presence of a timestamp and the digital signature prove that this certificate is valid and has been generated by a trusted third party. So all that is needed here is that A and B must actually trust the certificate authority to generate the certificate, but then the certificate can be valid at any time without having to go again to the certificate authority. It also makes this system scalable in that you obtain the certificate once and then no traffic actually goes to the certificate authority anymore. And so you don't require it to handle that much traffic all the time. So last thing we will discuss today is what actually is in this public key certificate. Okay, there is a standard that specifies this information, and it's called the X509 certificate, and there has been 3 versions of it. All the versions have basically the same idea. We had discussed it before. Whenever you want to obtain a certificate from a certificate authority, you present your information to the certificate authority. This is basically your public key, the algorithm that was used to generate this public key. So is it a Diffie-Hellman public key? Is it an RSA public key? What exactly is it? And your ID, your URL or your ID in the system or whatever. The certificate authority will hash it, okay, and will obtain the message digest. So this is the hash of the certificate, okay? And so the certificate authority will take this hash and will encrypt it with its own public key and will provide this encrypted hash to the entity or to the website that wants it, okay? And so whenever you want to verify that server or this website, you will ask for the certificate. So the website will give you the certificate itself, which includes all the information and the encrypted hash that was generated by the certificate authority. And you will take the encrypted hash and you will decrypt it with the public key of the certificate authority, which obviously is widely known. And then you will take the message, the certificate itself, which is just public information, and you will rehash. Then you will compare the two. If they match, then the hash must have been encrypted with the private key of the certificate authority. Then you have verified the digital signature in this case. So the X509 certificates include all the information that you see here in the slide. First of all, the version, is it version 1, 2, or 3? Then there is a serial number for the certificate itself, and the serial number is unique within each certificate authority. There are many of them around the internet. Okay, then the signature algorithm identifier, which algorithm was used to sign it. Okay, the issuer name is the name of the entity that is actually obtaining the certificate. The period of validity is when it is valid from. The issuer name is the name of the certificate authority itself. Okay, the subject name is the name of the owner of the certificate, who the certificate is issued to, and the public key info of the owner, the public key of the owner basically, and how it was generated and the parameters and all of that. Okay, so if it's RSA, then you need N, for example, the modulus. And then there is an issuer unique identifier and the subject unique identifier. These are available from version 2 and upwards. These are identifiers for the issuer and the subject. So in addition to the names of the issuer and the subject, there is also a unique identifier for them. In version 2, there are something called extension fields. And finally, the signature itself of the hash of all the fields in the certificate. So you hash all the fields and you sign them. The notation used for a certificate is this one. This means that this is the certificate of A signed by CA. Okay, so now this is what it looks like. So this is all the information: version, serial number, a signature algorithm, issuer name, period of validity, subject name, subject public key info, unique identifiers and extensions, and finally the signature. The certificate authority will also maintain something called the revocation list. This is a list of the certificates that have actually expired. And so you can check the revocation list to make sure that the certificate is not in it, to make sure that it is valid. Okay. Okay. So in the internet, there are actually many certificate authorities, and you have no reason to trust all of them. Maybe you trust only one. And so if you obtain a certificate from a certificate authority that you do not know, how would you actually trust it? If you have, for example, entity X, and entity X has a certificate from certificate authority 1. And then there is entity Y, and it has a certificate from certificate authority 2. Okay. X has no reason to trust CA2. It only trusts CA1. Y has no reason to trust CA1. It only trusts CA2. So when they exchange the certificates with each other, why would they trust it? It could be a fake certificate. So there needs to be a solution in this case so that X and Y would trust each other's certificate authorities. X would trust CA1 and CA2, and Y would trust CA1 and CA2. This is solved by having the certificate authorities themselves exchange certificates with each other. So there would be a certificate of CA2 that is signed by CA1, and there would be a certificate of CA1 that is signed by CA2. And they would have each other's certificate as well. So there would be a certificate here of CA2 that is signed by CA1, and here there would be a certificate of CA1 that is signed by CA2. So whenever the X and Y want to authenticate each other, they will send each other certificates, and they will send the certificates of the certificate authorities as well. So X will send to Y the certificate of X signed by CA1 and the certificate of CA1, okay, signed by CA2. It will send that to Y. So now Y has a certificate of CA1 that is signed by CA2, and Y trusts CA2, so it will now trust CA1 as well. When Y wants to authenticate itself to X, it will send the certificate of Y signed by CA2, and will send also the certificate of CA2 signed by CA1. And X trusts CA1, so it will trust this certificate as well. You can form what is called the certificate chain to authenticate anyone who is part of any certificate authority. Let's say, for example, A is acquiring the certificate of B, then it will get the certificate of B signed by Z, then the certificate of Z signed by Y, the certificate of Y signed by V, V signed by W, W signed by X, and A trusts X. So now the chain is complete. If B is acquiring the certificate of A, then it is the certificate of A signed by X, certificate of X signed by W, W signed by V, V signed by Y, Y signed by Z, and I trust Z. Okay. Every certificate authority will maintain two lists. One is called the forward certificates, and one is called the reverse certificates. Forward certificates are the certificates of X generated by other CAs. So the certificate of X signed by Y, the certificate of X signed by Z, the certificate of X signed by W. And the reverse certificates are the certificates generated by X that are certificates of other CAs. So the certificate of W signed by X, V signed by X, Y signed by X, and so on. So they will maintain these lists so that they can actually provide a certificate chain to anyone who actually requires it. Okay, and finally, these are the certificate extensions that are available in version 3 of the X509. There are key and policy information, some attributes to the subject and the issuer, and some path constraints as to how the certificate chain can actually be formed. That's it. At this point, we have seen how you can authenticate a server. So you know how you can authenticate a server by obtaining its certificate. And in the next lecture, we will see how a server can actually authenticate the client as well.